All right, next we're going to do this tabular with context one. So they give us a table. They tell us b prime of t. Where is it? Oh, sorry. So the radius, it's the rate, the radius is increasing. So b prime of t, rate, the radius is changing. And then that's in feet per second. So now we're going to find b double prime of 9, which means I need to take another derivative here. But since they only give me a table, notice how it says approximate. So we're approximating a second derivative, which just means I'm going to use a slope formula where 9 would fall. So 9 would be right here, which means with my slope formula, it's going to be 0.7 minus 1.5 divided by 10 minus 8. So that's going to be negative 0.8 divided by 2, which is negative 0.4. And then we need units here, so we just took another rate, so it's going to be feet per second, or feet per second squared. And then the meaning of this is just going to be the rate, the radius is changing is decreasing at a rate of 0.4 feet per second. So the decreasing takes care of the negative. All right, so now they want us to evaluate the integral from 0 to 10 of b double prime of dt. So looking at this, we should be using the first fundamental theorem of calculus. So we know this should equal b prime of 10 minus b prime of 0, which is just going to equal 0.7 minus 4.2. And then that's just going to equal, hold on, I don't know what that equals. Negative 3.5. And then we need our units here. So we took the antiderivative of b double prime. So it's just going to be b prime's units, which is feet per second. Give me 1 second. All right, C. Oh, shoot, I forgot to do part for B. The next part of this wants us to explain the context of this in relation to this problem. So essentially what we did is we took a rate, we went back a rate from the second, and we know our units were in feet per second. So now we got to relate this back to the ball and what this problem was all about. So we know we just subtracted two rates. Hold on. So we went from 0 to 10, So it's just going to be the rate the ball was being inflated decreased by 3.5 feet per second from 0 to 10. All right, C wants us to estimate the radius of the ball at time t equals 1.5 using the tangent line approximation at t equals 1. And then we got to figure out if it's greater or less than the true value. So what we're going to do, notice they tell us at t equals 1, it's 5 feet. So I'm going to have y minus 5 equals, I need whatever the derivative is at t equals 1, which we can see is right here because that's b prime. So it's going to be 3.2 x minus 1. So that's our tangent line. So now if I want to approximate 1.5, I just plug it in. So that becomes a half. Half of 3.2 is going to be 16. So y minus 5 equals 16. Not 16, 1.6. Then I have to add 5 to both sides. So y is going to equal 6.6. And then let's make sure we don't actually write it's equal to, because we just approximated using it, a tangent line. So really what we're going to say is b of 1.5 is approximately 6.6 feet. Since it's just b, not b prime, that's why it's going to be feet. All right, now we need to figure out if it's an underestimate or an overestimate. That's where we got to read our problem again. It tells us it's concave down. So if you think about a concave down function, any tangent line you draw is going to be over. So we can just say overestimate because b is concave down. That's all the justification we need. All right, write Riemann sum 5 subintervals. So I'm going to do that up top. Write Riemann sum means start from the right. So I'm going to evaluate from 0 to 10. That's what it was asking, right? B prime of t dt is approximately, because Riemann sums, 0.7. The change from 10 to 8 is 2, plus 1.5. Change from 8 to 6 is 2, plus 2.1. Change from 6 to 3 is 3, plus 2.6. Change from 3 to 1 is 2, and then 3.2. Change from 1 to 0 is 1. I'm going to leave that unsimplified, but it doesn't matter. You can simplify it if you want. I suggest you don't, though. And then it wants the meaning of this. So our meaning for this is going to be, so we just took the antiderivative of the rate. So we should be left with just feet here, because I got rid of that rate. So we're going to say the meaning of this is the radius of the ball increased by that many feet in 10 seconds. I guess you should say the first 10 seconds. Then it asks us overestimate or underestimate. Again, it's still concave down, so it's still going to be an overestimate. Because if we think about it, concave down for b means b prime is a decreasing function. So we think about a decreasing function. And then we did a right Riemann sum. I lied, it's not an overestimate. Concave down, decreasing. So if you draw your right Riemann sums, notice how they're all underneath, so it's going to be an underestimate. So on these, I would always draw the picture. They only tell us it's concave down. You have to use your chart to know it's decreasing. Draw the picture. Don't be dumb like me and make a mistake. Decreasing function, right Riemann sum, should be an underestimate. And then our reasoning is going to be because it's a right Riemann sum. And a decreasing function. Find the rate at which the volume of the ball is changing with respect to time at t equals 1. So for this one, we got to know what volume even is. So the volume of a, what is this, a sphere? So volume of a sphere, I'm going to do this at the bottom, I believe is 4/3 pi r cubed. So if I take the derivative, dv dt equals 4 pi r squared dr dt. And if I want to see where this happens at t equals 1, we know from up here, when t equals 1, our radius is 5. So I'll just plug everything in. dv dt equals 4 pi. Radius is 5. And then at t equals 1, I need dr dt, which is b prime. It should be that 3.2. And I'm going to leave it like that. I'm not going to simplify it. But think about volume. Its volume's got to be feet cubed, but it's over dt, so per second. All right, G. Is there a time t where b prime of t equals 2? So this one's a little tricky because it's asking about b prime of t. Normally you think mvt when you see a derivative. However, looking at our table up here, it's all about b prime t. So it's going to be ivt for this one. And then let's check. So for it to use ivt, it's got to be differentiable. So you can say, since b prime of t is differentiable and therefore continuous, ivt applies. Now we just have to find a spot where the y values have to pass through 2. So if we look up here, 4.2 to 3.2, no. 3.2 to 2.6, no. 2.6 to 2.1, no. But right here, to go from 2.1 to 1.5, that does have to happen. So I'm just going to write, thus, b prime of, it happens in between 6 and 8, so b prime of 6 equals 2.1 is greater than 2 is greater than b prime of 8, which equals 1.5. So there must exist a time t where 0 is less than t is less than 10, such that b prime of t equals 2. And that's our explanation using IBT. Now the next one wants us to explain why there is a time. That should be your Q, it's a theorem. But this time it's b double prime t. So b double prime t, that's going to be our MVT. So our explanation on this is since b is twice differentiable, and therefore continuous, MVT applies. Since now we have to find a slope formula where we're going to end up with negative 0.3. So if I look at this, it looks like it would happen at these same points anyways. So if I subtract these two, so let's think. 1.5 minus 2.1 over 8 minus 6, I'm going to end up getting negative 0.6 over 2, which equals negative 0.3. There must be a time zero is less than t is less than 10, such that b double prime of t equals negative 0.3. All right, last, erase all this. Use a left Riemann sum to find the average value of b prime of t. So average value of a function should be 1 over b minus a, so 10 minus 0 times the integral. So really I just need to do a left Riemann sum here, so 1 over 10, it's approximately 1 over 10 times left Riemann sum, so 4.2 times 1 plus 3.2 times 2 plus 2.6 times 3 plus 2.1 times 2 plus 1.5 times 2. And since this is a Riemann sum, make sure you have that approximately. Then the average value of that would still just be in feet per second.